So the next subtopic of this unit are solutions. So let's get the obligatory definitions out of the way. A solution is defined as any type of homogeneous mixture. Homogeneous means simply that the composition is the same throughout the entire thing. It consists of two parts. Part one is a solute. These are the substance or substances that are being dissolved. Typically that means they are present in a much smaller amount. And the solvent, by definition, is simply the substance that is present in the larger amount. So it's not that something, that solvents make the solutes dissolve. They both interact with each other. The solvent is simply the one that is present in the largest amount, and I will say that usually it is present in a much, much larger amount. And this is a phrase you will hear a lot, aqueous solution. And I will tell you that when you pen going here. When you see this AQ written in a chemical formula, that's telling you that that species is dissolved in water. All right, so there's two things that, at least three things that are used to describe a solution. The solvent, the nature of the solvent, let's say that it's water, the identity of the solute, and then the next thing is the concentration. This is a measure of the number density of the solute is there. And I think most of you probably have a good feel for what concentration actually means. Now, molarity is the unit that chemists prefer for concentration, and its definition is this. It is the moles of solute divided by the liters of solution. Now, a couple things. These specific units are important. That the volume has to be in liters. And the other thing is that it is specifically the volume of the solution and not just the solvent, because those two aren't always exactly the same thing. So let's go back to our dextrose here, except in this case we are looking at a intravenous injection of it. This particular bag, the volume of 100 milliliters, contains 5.126 grams of dextrose. So what is its molar concentration, which is kind of how we say that. And this is just a pretty simple application of that definition, but beware of the units and the quantities. So the first thing is that you need to know not the mass of the dextrose, but its amount, the number of moles. So hopefully now you're getting even more comfortable with mass to mole conversion, and you can figure out that 5.125 grams corresponds to 0.0284 moles of dextrose. And from here on in, you can just plug and chug into the definition. So we've got 0.0284 moles of dextrose, and again, don't forget the solution has to be in liters, and remember that milli equals 1/1000th, and 1 liter is the same as 1,000 milliliters. So that is a really common mistake that I see, that you do not convert the volume into liters, and that's something that you need to do. So to review, broadly speaking, or not broadly speaking, for molarity, so let's look at some units here. So if you have the solution concentration in molarity, and you have the volume in liters, that product will give you the amount. In a much more general term, concentration times volume gives you some sort of amount. And this is quite possibly one of the most important strings of characters in this class. Concentration times volume gives you amount. So that is the relationship between those three quantities. They're related. So if I give you any two of them, you can, with the appropriate algebra, figure out the third. Again, remember, so molarity times liters equals moles is probably also another easy way to know it, because those are usually the units that you'll see it in. So write that down, say it a couple times, get it into your memory. Now, so let's say that of that 100 milliliters in the bag, 75 of it was administered to the patient. In that case, how many moles of dextrose did they receive? Again, a fairly straightforward application of that concentration times volume gives you amount, except it's in the other direction. I've got the volume in liters times the concentration in moles per liter, or molarity. So liters cancel, we have moles. So that is 0.021 moles of dextrose were administered in that 75 milliliters of solution. To get one more little practice in, so what mass of dextrose does that correspond to? How would you do that? Again, so the molar mass from a couple slides ago is always the link between those. So we've got 0.021 moles of dextrose times 180.16 grams of dextrose divided by 1 mole. That gives us 3.8 grams of dextrose. And so these are pretty straightforward problems, and the idea is that with a little bit of practice, you should be able to do those without a whole lot of conscious thought. So make sure that you do that. All right, so there are some other concentration units as well that you might run into. So I'm just going to review a couple. So molarity is the big one, at least as far as what chemists use, and that is denoted by a uppercase M. Molality, so be careful, they are one character different. The R and the L are switched. And that is denoted with a lower m. And percent by mass, percent by volume, mass volume percent, parts per million, parts per billion. I grouped those together because they are very similar. So I want to talk about the units of all of these, or most of them, one at a time. All right, we talked about molarity. So that is moles of solute over liters of solution. Molality, this is defined in terms of the moles of solute, but the mass of the solvent. Some differences here. Number one, in the denominator we have a volume component here, and we have a mass component here. This one's defined in terms of the solution. This one is defined in terms of the solvent. So those are important distinctions. All right, percent by mass. This is something that you probably have an intuitive feel for at this point in your lives. It is merely the mass of the solute divided by the mass of the solution times 100. Now, given that, and it doesn't actually really have to be grams. As long as they're the same unit of mass, it could be ounces and ounces, it could be tons and tons, because they cancel out. Parts per million is exactly the same concept, except the multiplier at the end here is a million. And this is used for much more dilute solutions than percent mass is used for. And lastly, parts per billion, again, same concept, mass of the solute divided by the mass of the solution, except now we're multiplying by a billion. And so these are used, this concentration unit is made for ridiculously small concentrations. Things, like, so the allowable concentration of lead in drinking water is expressed in parts per billion. Right. And the other thing to note for all three of these they're technically unitless because the mass unit and the numerator and the denominator cancel out. So their units are just percent or ppm or ppb. All right. So let's go through a couple of examples. Oh, sorry, I got two more. So percent by volume is a less common one, at least in the scientific field. And it's just the volume of the solution, the volume of a particular solute divided by the volume of the solution. And I take that back. This one actually is used fairly regularly in the food and beverage industry. And here is the one that is not used very much at all, and that's mass volume percent, and that is the mass of the solute divided by the volume of the solution in milliliters, and both of these are times 100. Now let's do some examples.